Right. It's our pleasure to host Dr. Giray Yağlıkçı. Giray is a tenure track faculty at CISPA in Germany. So he graduated from Temperature University, and then he completed his PhD in ETH Zurich with honor. He works in modern DRAM-based systems and especially in hardware security as well. Again, we welcome Dr. Yağlıkçı. So I know that you're going to introduce yourself, so I'll just stop.
Thank you very much. Yeah, thanks a lot for organizing this talk. It's my pleasure to talk at Bilkent University. I know that there are a lot of great minds here. I'm really looking forward to hearing your feedback on my research and also for future collaborations. As Can Hocam said, I'm Giray, and today I'll talk about making DRAM available again. Okay, let's dive into that. Okay, the first thing, it didn't work. Okay, nice. Doesn't work anymore, so this is useless. I can just hit there. Okay, so this is my brief self-introduction. I'm a tenure track faculty at CISPA, and I spent some time in software research group, and before that I was part of Kasırga Lab in Tobedi. And I mostly worked on computer architecture, memory subsystem, hardware security, dependability, sustainability, hardware-software cooperation, and testing and verification. And now I'm part of a branch of Helmholtz Institute. So this is a type of organization called Non-University Research in Germany. Some examples that you might heard of is Helmholtz, Max Planck Institute, and Leibniz Association. So these are not universities, but they do research similar to BITAC here. And this is where I work. So this is CISPA, Center for Information Security, Privacy, and Accountability. And it's in the west side of Germany. So it's in sort of like middle of nowhere, but at the same time, it has good connections to some major destinations, including Antalya, if you take a flight. Okay, so this is where we are in CS rankings. And if you filter CS rankings purely on computer security, then it has a top place. And if you go for architecture and security, then it goes a little bit low, but it's still in the like top 20. There are a lot of people doing great research, and I just joined recently, so I'm not taking credit for any of that success. But yeah, so I'm building my team nowadays, and I'm looking for motivated researchers in different levels to do research. And my research goal is to enable systems to scale securely and sustainably as chips get denser and many users use these systems. And on that, I'm going to talk about RowHammer today. Did people hear about RowHammer here? Okay, that's great. A bunch of people know about RowHammer. So here we talk about the memory safety and security. So I'm going to talk about DRAM read disturbance as a security problem. So this is a little bit background. I hope I will give this background thoroughly. So imagine that this is your memory in your computer. Just try it again, but it doesn't work. Okay. And you perform an access to a memory location, you read or write, and you observe that there is a bit of data changing in some other location that you didn't access. So you do not want this kind of thing to happen because it can lead to data loss or corruption in your system. Am I blocking it too much?
You are.
Okay.
Good.
Sorry about the tripod. So it can lead to compromising applications correctness. It can be used against you to leak your private information or to take over your computer. And there are a lot of works in the literature showing how practical it is. But in a nutshell, we can say that having this DRAM read disturbance problem, changing a bit in a location that you didn't access, can lead to data integrity or confidentiality issues. And there are many techniques in the literature today that mitigate DRAM read disturbance and avoid data integrity and confidentiality issues. but it comes at the cost of availability. And if you recall, the three pillars of security are confidentiality, integrity, and availability. So it becomes really hard to achieve all three of them. So today we will more focus on availability of memory. This memory isolation or the mitigating this read disturbance is a challenge in today's systems, and this is why. As prevalent memory technology today, we use dynamic random access memory, or in short, it's DRAM. And DRAM stores data in the form of an electrical charge on a capacitor, and it leaks charge over time. So it's a volatile memory technology, and you need to periodically refresh it to make sure that your data has integrity. And there's this phenomenon called DRAM read disturbance, where you access a DRAM cell repeatedly, and it leads to exacerbating the charge leakage in nearby cells. And as a result, your volatility gets worse, and you can lose your data. And it can be exploited in many different ways that I talked about earlier. So to give more background, I'm going to talk about how DRAM looks like and how we access data in DRAM. So this is a two-dimensional cartoonish picture of a DRAM array. So each circle here is a DRAM cell, and the rectangles down there are differential sense amplifiers that we call row buffer. It's kind of a latch. To access data in a particular location, you need to access data in a DRAM row granularity. This is how DRAM works. So you need to perform an operation called activate, so that you can fetch the row's information down to the row buffer. And then you perform reads or writes to particular sense amplifiers from that row buffer, so that you can serve your read and write requests. And then once you're done with data in that particular row, you need to pre-charge the whole array, prepare it for the next activation to another row. And these operations are quite time-consuming, especially activate and pre-charge are quite time-consuming operations. Each of them takes around like 15 nanoseconds or 10 to 15 nanoseconds in today's chips. And it's a major contribution of the memory access latency. This is another cartoonish picture of how a DRAM array looks like. So as I said, you access data in a DRAM row granularity. So each rectangle here is a DRAM row here. It has around like 8,000 cells. 64,000 cells. To access data, as I said, we need to activate a row, or we open the row in other terms. Once we're done, we close it, right? So if you perform this open and close operation many times, then we observe bitflips in nearby locations in the rows that we do not access. And this is called RowHammer. And it's a prime example of a generic term of DRAM read disturbance. You basically read particular locations and you disturb data in other locations. And this is practically used in break-in memory isolation and leading all those problems. Here for a little more terminology, the row that we repeatedly access is called aggressor row, and the rows that are affected are called victim rows. And to mitigate RowHammer, it's very easy, actually. You just need to perform an operation called refresh that's already performed periodically in DRAM devices. So you basically refresh victim rows before they experience any bitflips. And as a result, you restore their charge, you reset the leakage happened so far, and then you're good to go. But the tricky part is to decide which victim row to refresh and when to refresh. And there are a lot of works in the literature to find some sweet spot of that. This RowHammer phenomenon is first shown as a widespread problem in 2014 by this paper. And then 1 year later, Google Project Zero showed a quite reliable way of exploiting this physical phenomenon in the system level and gain privileges, get the root access, and hack computers, basically, through inducing bitflips in the page table entries. And it was in 2015. And a decade fast forward, a lot of things happened. People dived into understanding this RowHammer phenomenon more. They worked on how to mitigate it, how to exploit it. And there are a lot of works in the literature. I'm not going to show all of them, of course. But this paper particularly shows that even after a decade later, there's another Google paper here that shows how to bypass Samsung's best practice on mitigating this DRAM read disturbance. So it's still an ongoing thing. And here is why, actually. So DRAM read disturbance remains as a critical challenge because of technological scaling. So again, another cartoonish picture, each circle assume that they are DRAM cells. So with technological scaling, we achieve higher density in a particular millimeter square. You put more gigabytes. And to enable that, you need to shrink the size of your DRAM cells. Volatility gets worse. And they get closer to each other. So when you access them, you disturb more cells. And as a result, if you look at the data in the literature, this is experimental data showing the minimum activation count to induce the first read disturbance bit flip. It's decreased a lot in less than a decade, actually, more than 2 orders of magnitude. And DRAM cells become increasingly more vulnerable to read disturbance, and this causes the mitigation mechanisms to be more aggressive and consume more time. So it reduces your performance, it increases your energy consumption. You need to maintain a lot of metadata, so it becomes a problem. Okay, so industry also looked into that, not academic research only. So in the past like half a decade, JEDEC formed a RowHammer task force. JEDEC is the consortium that decides these memory standards that you recall with the names like DDR3, 4, 5, right? Or HBM. So this JEDEC decides like what how they look like. And the manufacturers, the DRAM manufacturers, especially Samsung, Micron, and Hynix, changed their attitude. In the beginning, they were in more of a denial kind of attitude. They were claiming that there's no problem. And then after a lot of research, they started coming up with solutions. And an early secure solution emerged from a small memory company called UpMem. Maybe you heard about that company by their efforts on processing in memory. They also looked into RowHammer, and we actually did the security analysis of their patented solution in 2021. And then we started seeing a lot of papers from Microsoft, SK Hynix, Samsung, NVIDIA, Google, and yeah, and then the things are still going on, and this is just like a small sample set of papers. Like there are more papers in the literature. I couldn't fit everything here. In 2024 April, it was like a few weeks before I defended my PhD thesis, actually, that the JEDEC documents, yeah, one of the JEDEC documents get updated. And it's in the recent update, we saw the first promising mechanism or the framework after the discovery of RowHammer to mitigate RowHammer. It's called PRAC, per row activation counting in DRAM. So today I'm going to talk about that a lot. So I'll first explain how it works, and I'll talk about the outstanding problems it has by design, and then how we solve it. Okay, so but just taking a step back, the key insight of this talk is that mitigation mechanisms provide strong data integrity at the cost of availability. So it causes a lot of performance and energy issues. And we tackle those issues in 2 different papers that we published during my postdoc at ETH. And I'm going to talk about these 2 papers if we have enough time. Okay, so the first paper is Chronus. It was published in HBCA 2025, about like a year ago, where we look into the design in the JEDEC document and make the best sense out of it as we can. And then we implemented in a simulation environment and investigated the outstanding problems and solved them. So this is how it works. So this is again like a very high level representation of a DRAM array. So you have the DRAM rows and you store your data. There's like ones and zeros over there. And what this, I will call it framework or just prac, activation counting. So what it proposes or explains in the document is that you put a counter just inside the DRAM row, or you just expand DRAM row by a few bits so that you can maintain the activation count of a particular row within the row. Basically, once you activate a row, you increment the activation counter here. And at a given time, you access this counter and you know exactly what the activation count of that row is. And you decide if you want to perform refreshes in nearby rows at that time very accurately. Okay, so yeah, the activation count increases, and as a result, you perform refresh. So let's look at how this works now with the timing on a timeline on the bottom. So on the left we have the processor, on the right we have the memory. So maybe I should say first that in this protocol, all DDR protocol, HBM, everything, it has this general assumption of processor, the memory controller inside the processor being the master, and the DRAM chip being the dumb device as like quote unquote slave. So the memory controller decides what will happen at what time very precisely, and memory is expected to just obey those commands and perform them. So memory itself does not do anything smart. But in this new update with the per activation counting, where we put the counters inside the DRAM rows, now we need to put some smartness inside the memory chip so that it can increment the counter when needed, and when the counter value reaches a threshold, it can trigger some refresh operations. And it's against the general like historical evolution of these protocols. So here I'm gonna explain like how it works. So from processor side, you send an activation command to activate a row inside the DRAM. And then as a result of that, the counter corresponding to that row is incremented inside the DRAM chip automatically. And this happens several times. And at some point, a counter here reaches a threshold called backoff threshold. And once the memory detects this counter being incremented and reaching the backoff threshold, it says, okay, I need some time now to perform the refresh operations. And then it asserts a signal from the memory back to the processor called alert backoff signal in the standards, telling that, okay, just stop, back off a little bit. I need to perform some refresh operations. But it's not that simple because the processor already has a complicated scheduling algorithm that needs to, serve some requests because all the loads and stores from your application are waiting there. So the processor is allowed to perform a normal traffic about like 180 nanoseconds at this point, and it can perform additional activations during this time frame. And then there's a recovery time where the processor sends a special command called RFM, refresh management command. This command allows the memory chip to it provides the memory chip with the necessary time to perform several refresh operations. In the current standards, it's enough for refreshing 4 different rows. And by receiving this RFM commands, the memory can refresh those victim rows. And you can configure the mechanism to send like n different RFM commands back to back. So it can be 1 RFM command, 2 RFM commands, or 4 RFM commands. It's basically like as the number n increases, the mitigation mechanism becomes more aggressive. But now your requests are delayed for longer time. And once that happens, there's also a delay period during which the memory is not allowed to send another backoff to the processor. And it is there to make sure that the memory requests are served in a nice way. Okay, so this is how the mechanism works. Maybe I can stop here a little bit and take your questions. If there's something unclear, maybe I can answer that first, because I will build on this mechanism in the rest of the talk. Sure.
Well, the main problem is the rows that are accessed frequently, right?
Yes.
It affects nearby rows. Will some kind of caching help here? I mean, if you know some rows are accessed regularly, you can move them.
Yes, so it's
nearby ones, so maybe they're not that much affected in the original DRAM.
That's correct. Yeah, caching definitely affects. So we are already incentivized to do caching over there anyway, right? So if we cache some data, if we frequently access that, we want it to be inside the processor. We don't want off-chip data movement anyway for energy and performance reasons. And we do our best in our systems today. It doesn't work perfectly all the time, so that's like one caveat. And the second one is if you consider the malicious scenarios, like if this happens by itself, it's like a reliability problem. But if it can be practically exploited by some malicious users, then it's a security problem, right? So papers in the literature, like several papers, show that there are like several different practical ways of bypassing caches. So you can craft a memory access pattern to force evictions in caches, and it leads to like writing back in the memory or evicting that cache basically, and then you need to access memory. Or there are other papers that propose to perform those memory access patterns from the DMA, direct memory access controller. And you can do that from like even remote locations, like using the network packets, for example, or using some requests coming from GPU. And those methods can help bypassing caches. So the security problem remains intact. Yeah. Please.
I have a similar question. Roll buffer is also some kind of a
Cache, yes. Yes.
I'm not talking about memory.
Yeah.
So if my algorithm respects special coherences or iteratively accesses consecutive elements, so if you only process a row buffer and then another row buffer.
Yes.
Do you still have that problem?
Yeah. Again, the same thing. So improving the
switch between different row buffers.
Yeah. So basically, the row buffer is. So row buffer has the data as long as you keep the row open.
Yeah.
And it is. So it works as a cache in that case. Like you hit the row buffer and then you can fetch the data very quickly. You don't have to activate another row. So it's great for performance reasons and energy reasons. But at the same time, keeping the row open for longer time, like for very long, is also not really desired in modern systems. Like because it keeps consuming energy. It's a part of like a SRAM array in structure similarly. So to avoid that energy consumption, current memory controllers usually apply a timeout protocol. So after some time, they close the row. And when you craft your memory accesses, you can put some intentional delays in between, and then you can force access in different rows. Yeah, so that's how they do usually. Sure. Okay, I'll continue. So we identified two major outstanding problems of this design. One of them is, I'm going to talk about this in detail. So it causes some critical DRAM timing parameters to increase, and it leads to delays to your memory requests. And as a result, you get some significant performance overheads. Yeah, at even high thresholds that are like relevant to today's modern memory chips. Okay, so let me explain how it works. So again, we have the DRAM row, we have the data, we have the counter. So the activation counter of a row is updated while the row is being closed. And it has a very naive reason, actually. So you activate the DRAM row for accessing data, right? So you don't activate it for no reason. So once you activate it, you want to immediately access data so that you can serve your request fast. And basically, you serve the requests, you serve all your reads writes. And then once it's time to close the row, you need to update the counter. And to update the counter, you basically need to read the counter value to some central structure, some circuitry inside the DRAM chip, increment it by 1, and then write it back. And this increases the time you spend for the particular pre-charge operation, the operation you use to close the rows. And once you look at the specifications and how much that value changes, it corresponds to 140% increase in this particular timing constraint. And this is a full list of the timing constraints that this mechanism affects. So TRP is for closing rows, TRS is for charge restoration. I don't need to get into details actually. As a result, this TRC is a key parameter. It's basically the delay between your two activations. It's called row cycle delay. Once you add those up, basically it not directly add up, but yeah, once you do the math, it corresponds to around like 10% increase in the row cycle time. So between the time between activating a row and activating another row increases by 10%. And that leads to some performance issues that I'm going to show next. And the second issue is a new vulnerability to a particular memory access pattern called wave attack. And it limits the scalability of the mechanism as proposed. And it leads to high performance overheads in future DRAM chips. Okay, so let me talk about the wave attack a little bit. So this is the worst case access pattern that we identified for UpMAM's mechanism actually in the past, but it applies to PRAC as well. So it's kind of an attack that you concurrently attack to many rows, like 100 of rows, let's say. You increment their activation count by keeping a low profile, and you do not trigger any refresh operations to some extent. And then you keep accessing to them in an aggressive way. And it overwhelms the system, basically. The system becomes quite unresponsive to perform all those refresh operations. And if your mechanism is not designed for that, as we see in the Prax case, then it leads to not performing enough refreshes and can lead to bitflips as well. So you need to configure your system in a more aggressive way than it's supposed to. So we sweep different parameters of this wave attack, and we try different configurations of the PRAC to be complete. And we find the worst possible activation count an attacker can achieve for a given configuration. And this is the results. So on the x-axis here, we have the back-off threshold. Basically, this is a threshold that you can, it's a knob you use to configure your PRAC mechanism. And going from left to right, you perform less frequent back-off signals. So the leftmost bar is the most aggressive one. And on the y-axis, we show the highest activation count that can be reached by an attacker. And lower is better because we do not want them to reach higher activation counts. And different colors are for different configurations of PRAC. The numbers are 1 to 4 that correspond to the number of those RowHammer commands that are sent at once. Okay, so maybe I can just go to the takeaway here. So maybe I highlight. Okay, so let's highlight this point. So for these bars, this is the most aggressive configuration of PRAC that we can do. So the back-off threshold is 1, meaning that after every activation, you send a back-off signal. And once you do that, the whole mechanism works over there as I explained, right? So the memory controller has some additional time to perform some normal traffic. And then you have the RFMs coming and rows being refreshed. And then you have the delay period that you cannot send back off. So we simulated all that in an analytical model. And then we reached to the conclusion that in the most aggressive configuration of crack, for the most aggressive backoff threshold of 1, an attacker can reach to an activation count of 19 for a given DRAM row. And if you go for like less aggressive configurations, the bars increase, so the attacker can achieve higher activation counts. So so as a result, basically, this mechanism is good enough to protect your device. If your device is as vulnerable to RowHammer as like it experiences bitflips after 20 activations, because you can limit it there. But for that, you need to send a backoff signal after every row activation. That causes a lot of delays, of course. Yes.
Sorry to interrupt. I have I have a question on what does the highest activation count mean? It's activation in victim row or like the hammering we do on the aggressor row?
Aggressor row. Yeah, so if you activate the victim row, actually we end up refreshing it. So it doesn't work in favor of the attacker. So this is like what the attacker can achieve, basically. Okay, so we looked into the performance impact of this in a simulation environment for different workloads and for different configuration of the mechanisms. I'm not going to get into details of these, but like these are just different bars in the same plot. So on the x-axis, we look at the RowHammer threshold. It's a reversed axis, like it goes lower as you go from left to right. It's because like the RowHammer vulnerability increases, so you experience bitflips at lower activation counts. And we of course configure the mechanisms for each RowHammer threshold over there. And on the y-axis, we have the normalized weighted speedup. It's normalized to the case that you do not have any RowHammer protection in your system. So 1.0 is the best result that we expect, of course, or we desire. But yeah, it's not easy to achieve that. And here are different configurations of the PRAC mechanism. And what we observe is that this 1024 number is a realistic number or relevant number for today's DRAM chips. And if you implement this mechanism in your today's DRAM chips and configure it for that, in common case, you have around like 6% performance degradation in your system just to perform those refresh operations. And I need to take it back. It's not because of refresh operations, actually. It's because of the DRAM access latency that is increased. I talked about 140% increase in one of the time parameters. So that that translates to 6% performance degradation when you do the simulation. And for futuristic DRAM chips, as the RowHammer threshold gets lower, we simulated different configurations again. And until the RowHammer threshold of 64, which is still quite aggressive, we do not observe like much difference in the performance degradation. So it's around like 6% again. But after that, things get worse. So we also investigated why they get worse. It's because after this point, to account for the wave attack, you need to configure your system, your mechanism too aggressively, similar to like one backoff after each activation, and as a result, you get huge performance degradations at that point. So these are two problems that the PRAC mechanism in JEDEC specification has, and we have two key ideas to tackle those problems. So the first one is concurrently updating counter while serving DRAM accesses. So we have two operations, and one is causing delays for the other one. So our idea is, okay, why not we do them in parallel? And it's a very like natural follow-up, I guess. And as a result of doing that, we do not increase critical timing parameters, in particular DRAM, the latency of closing DRAM row, or TRP. And as a result, we get rid of that 6% performance degradation. And we prevent wave attacks by providing DRAM chip more control over backoffs and preventive refreshes. In a nutshell, what we do is that we allow the DRAM to have more control in the system. we get rid of that delay period in the timeline over there, and as a result, the vulnerability to wave attack disappears, and we can configure our mechanism less aggressively than the original one. And as a result, we can reduce the performance overheads and enable better scaling. So the first part, how we do the counter update in parallel is like this. So in DRAM bank, we have a huge DRAM array. So it's like a gigabyte large array, let's say. And in the circuitry, it consists of many of these structures called subarrays. So in each subarray, let's say you have like 1,000 rows. I say let's say because it's not standard. It changes from chip to chip. It's around like 500 to 1,000 or maybe like 1,500 rows in a subarray. And then there's a local row buffer, and then another subarray, another local row buffer. So you can activate these rows, like a row here in this subarray, for example, and then another row in this subarray, and they can both be active at the same time because these circuitry do not, they're mostly independent from each other. And they just share the I/O. So once you need to use the I/O, you need to be careful about using them concurrently. But for counter updates, we do not need I/O. So what we propose is to put a counter subarray, a small subarray, where we just like coalesce all the counter values for all these rows in just a bunch of counter rows here. And it has its own row buffer, it has its own row decoder, the local ones, and it has its own increment logic. We have all details of that logic in the paper as well. So you can activate, maybe I should animate it. So you can access this regular subarray and access this counter subarray concurrently. So you perform the regular accesses from the regular subarray and counter updates here, and you can leverage the subarray level parallelism to perform that. So to animate, yeah. So basically, once you open a row, you also open a row in the counter subarray, access the counter over there, and during the time that you access the columns of this row in the regular subarray, you also access the counter value, increment it, and write it back. And it doesn't cause increase in the critical timing parameters. And as a result, we get rid of that performance overhead of 6%. And this is the full paper. So we show that the counter subarray incurs around like 0.5% area overhead per bank. And it induces around 19% energy overhead to open and close a row, which is later tackled by another paper. It's not our paper, it's just like in the literature. And it also elevates that 19% energy overhead. So today with that paper's contribution, our mechanism is like more promising. Okay, so this is the first part. And second part, yeah, go ahead, please.
Wouldn't the counter subarray itself be vulnerable to the attacks as well?
It is, yes. You still store the counter values in DRAM cells, so it has all the problems that the regular DRAM cells have. We also discuss how to protect those in the paper. So there are like more when your array is small, there are like very simple ways of protecting it. So here, for example, we have a row here and then another row here, right? So in total, let's say we have like 64 or 128 rows in this counter subarray. We basically can put some guard rows in between to put more isolation across rows so that we can elevate read disturbance. Or another way is that we can put an additional array of latches inside the row buffer so that whenever you activate a row, you can randomly select a row to refresh, and you can do the refresh operation in parallel as well. So these are some mechanisms that are already like proposed as RowHammer solutions in the literature we got from like other groups. They all apply to here because the main problem they have is that their area hardware complexity overhead usually are huge, but once your actual array size is like very small, their overheads are also small. So yeah, we discussed that in the paper. Does that make sense?
Yeah.
Okay. Another question? No. Okay.
Yeah.
Sure.
So, when you were showing the mechanism in like slide 40, of like serving requests concurrently, so it's cites something published in 2012. So was this like concurrent access? Like was this approach like proposed before RowHammer was discovered?
Are you referring to the
Like, I am referring to that SALP.
SALP? Okay, yes, exactly. So we basically apply that paper here, right? This is a case study for that paper. So that paper was published before RowHammer was discovered as like widespread phenomenon. Yes, that's true, and it was proposed for increasing memory bandwidth and reducing memory latency overheads, basically by access, because so in a DRAM channel or in a DRAM rank, you have like in DDR5 standards, you have 32 different banks. So you can concurrently access 32 different arrays. But within each bank, you have hundreds of subarrays. So if you can access all of them in parallel, then you have huge bandwidth. And yeah, that was the main motivation of that paper. Sure. Another question? Okay. So we also do another tweak on the existing prac mechanism that we call Chronus backoff, because our mechanism is called Chronus. Chronus backoff prevents the potential wave attack with two simple changes in prac backoff. So it allows the DRAM chip to dynamically control to the number of refreshes as needed, and it does not. But we achieve this by eliminating this delay period. So this is the timeline that I showed before. So we basically get rid of this, meaning that after receiving the second RFM command, DRAM is still allowed to send another backoff signal. And it comes with the cost of this like normal traffic in between, but then you can have more RFMs coming up. So once you enable that, so your memory scheduler might not work as good as like before, but you eliminate this like aggressive configuration of the RowHammer mitigation, and as a result, you alleviate a big part of that performance degradation. So that's the next thing: performance and energy consumption evaluation. So we look at Chronus by itself, that uses the like both mechanisms that the concurrent counter update and the Chronus backoff, our specialized backoff, and we also look at Chronus with Prax backoff, which is PB, and we compare this mechanism against like 5 mechanisms in the literature that shows the state of the art. And the first one is the performance results. Again, the same plot, RowHammer threshold gets lower while we go left to right. And we look at the system throughput in terms of weighted speed up on the y-axis. So these are the results, and different colors are corresponding to different mechanisms. Here is a highlight. So in the original prac, we had around that 6% performance degradation. So now that is reduced to lower than 0.1%, so mostly eliminated. And in an aggressive configuration, if you compare Chronus against the Chronus with prac backoff and prac itself, we see a huge difference in these bars. And also, yeah, so this shows that our modification to backoff pays off when the RowHammer threshold gets lower. And in all RowHammer thresholds, we basically outperform the all other mechanisms that represent the state of the art. Okay, so in summary, Chronus reduces Prax's performance overheads by concurrently updating counter and allowing the memory to be smarter. And we have a lot of details in the paper, so I don't have time to get into all of that, but I'm happy to talk about them after the talk. And this is the full reference paper, and it's also available on arXiv. And yeah, this is what we did in this paper. We analyzed the existing Prague mechanism and then identified two major weaknesses and solved them, and showed our results are better than the original Prague. And all of our artifacts are open sourced, available on GitHub, and also got the artifact evaluation badges. And this is an earlier version of this paper. I just wanted to put the reference here. So this is so the Prague update came in April, and in June there was a workshop called DRAM-sec collocated with ISCA. So we did the first analysis over there, and we also open sourced our implementation at that time. Actually, researchers from Georgia Tech, Google, some other places, I guess SNU, Seoul National University, they looked at our they like repeated our results and regenerated our results. They looked at our implementation. They figured out some bugs here and there. We communicated. Everything is solved now. So open source implementation is still available in the main branch of the Remulator. Okay. So this was Chronus. And if we have time, I'll also talk about the second paper, BreakHammer. Okay. So we are already like around 50 minutes, right? So maybe I'm gonna give the high level key idea over there and then just skip the rest. So this is the main analogy of this paper. The problem we are tackling here is the reduced availability of the memory device, right? So this is our inspiration called breakwater. It's a structure in civil engineering. Actually, there's a Turkish name over there as well, Dalga Kıran. So basically, you build this huge wall around coastal areas in coast to the open sea or ocean. Basically, once you have a lot of waves coming from the sea, and you have some marine, for example, inside your coastal area, you do not want them to put a lot of harm over there. So you want to mitigate the harm that they can cause in the sea. This is a nice structure that is used like a lot of places. And a lucky coincidence, the slide number is 61. So if anyone is from Trabzon, probably they're going to be quite familiar with this structure because of the crazy waves over there. Okay, so this is basically the structure that we got our inspiration from to reduce the overheads of RowHammer mitigation in our memory systems and improving the memory's availability. With that name, we put our paper's name BreakHammer. We break the hammer instead of water, enhancing RowHammer mitigation by carefully throttling suspect threads. And the problem we tackle is that RowHammer preventive actions frequently block the memory array. So it reduces DRAM's availability, so our memory requests get stalled. And once your loads and stores are stalled in your system, then your whole processor is waiting, idle, or there's a context switch, it performs something else, your application waits. And it reduces your performance, it increases the energy consumption of your system. And we do not want that to happen. So we reduce the memory mitigations performance, or this is our goal. And our key idea is to reduce the RowHammer preventive action count in our system without compromising system robustness. And we achieve it by doing this. This is our key mechanism, BreakHammer. In this hypothetical scenario, we have a multi-core system, and in different cores, there are different applications from different users. And it's not important, actually, if they're from different users. There are different applications in different cores, and in one of the cores, we have an attacker. And it performs a certain, it crafts a memory access pattern, applies it, and as a result, it tries to get RowHammer bitflips, or it tries to slow down your system. And we detect this threat as the suspect threat, and we reduce its memory bandwidth usage. And this is how we do that. We follow a epoch-based approach. Between each RowHammer preventive refresh action, we look at how each thread behaves, and we attribute some penalty scores to each of these threads. And as a result, we get these numbers, and we have a very simple logic over there that identifies suspect threads by looking at the anomaly across these threads. And once we identify a suspect thread, we do not allow the thread to access memory by reducing the cache miss registers it can allocate. This is the full paper. We integrate BreakHammer with it's by nature it's a mechanism that works ad hoc with existing RowHammer mitigation mechanisms. So we show that we can integrate it with 8 different mechanisms in the literature, but it can be integrated with more mechanisms, of course. We look at the performance and energy impact of this mechanism, and we compare it to these 8 different RowHammer mitigation mechanisms. And this is a nice result that I want to show. So here on the y-axis we have the preventive action count normalized to like a very low number as the baseline. And on the x-axis, we have the RowHammer threshold going from 4K down to 64. This is like a sensitivity study in a sense, but I take it as a insightful main result here, basically. So if you go with PRAC mechanism as defined in the JEDEC standards, you have this kind of curve. As the RowHammer threshold gets lower, you perform more RowHammer preventive actions, refreshes. And if you also integrate it with BreakHammer, then this blue curve goes down to orange curve. So we can reduce the number of preventive actions in the system quite significantly, around 34x in this point, for example. Okay, and it's the same scenario for like different RowHammer mitigation mechanisms as well. And as I said, like it immediately has impact on the memory access latency. So the black curve is the baseline where we do not have any RowHammer mitigation mechanism in our system. And the blue curve is a mechanism, in this case it's PRAC. And the orange curve is the mechanism integrated with BreakHammer. And here we look at the distribution. On the x-axis, we have the percentile of the memory access latencies, and on the y-axis, we have the exact number. So if you look at this point, for example, you can say that 50% of the requests are served within 200 milliseconds. Then you have PRAC in your system. But you can reduce it quite low. Unfortunately, I didn't highlight the exact number, so I don't have the exact number here, but you can see from the y-axis, you can reduce it a lot with BreakHammer. Okay, so it's the same scenario with like all 8 different RowHammer mitigation mechanisms. And when you look at the performance impact, we can increase system performance quite a lot when there is an attacker in system. So you have, let's say, 4 cores, and you have benign applications in 3 of them, and 1 core has the attacker. What you do is with BreakHammer, you reduce the memory bandwidth usage of the attacker thread over there. So it immediately opens up more fraction of the memory bandwidth for the other concurrently running benign applications. And you can increase their performance quite significantly. And this is the results for that. And the results are similar for different mechanisms again. I'm just going to flash these slides. And this is important, energy consumption. So again, as one of the threads do not access memory quite frequently, then its memory DRAM energy consumption is quite low when you enable BreakHammer. As a result, we reduce the DRAM energy consumption quite significantly. Again, the same scenario for all 8 different mechanisms. And these were the results from the case where we have an attacker in our system. So BreakHammer significantly reduces the negative performance and energy overheads of existing RowHammer mitigation mechanisms when a memory performance attack is present. and it accurately detects suspect threats and effectively reduces their memory interference. And we also looked into the case where we do not have attackers in our system, and we show that the performance and energy results don't go bad. And basically, we have like more analysis in our paper again. I encourage you to take a look at that or just talk with me. I'm happy to talk about it. So this is the full reference with the archive link, and this is summary, but I already gave the summary, so I'm not going to go through that. And our artifact is also evaluated in this case. We got the badges, and everything is available on GitHub. And this is the BreakHammer paper. So to wrap up, in a nutshell, RowHammer mitigation mechanisms promise data integrity at the cost of DRAM availability. And we have two mechanisms that I mentioned in this call. Chronus improves DRAM availability via implementing crack in a better way. And BreakHammer improves DRAM availability by reducing the memory bandwidth usage of the suspect threads. And with that, I'd like to take a step back and reiterate my goal. I want to enable systems to scale securely and sustainably as chips get denser and many users share systems. And for that, I'm planning the future works, basically. We have more vulnerabilities coming up in the literature. So this paper in Micro 25, it was like it was in October, so it was like 2-3 months ago. Showed that you can exploit RowHammer defense mechanisms to form covert channels and side channels in your system to tackle similar problems. Basically, we need systems that are more that are designed in a more harmonious way of hardware and software. So I have some works going on in hardware software co-design. It's like one of the motivations. We had another paper in Micro 25 showing yet another type of read disturbance called column disturb. In this case, you hammer rows, but in fact, in the circuit level, you swing the voltage on the bit lines, which are the columns in that two-dimensional arrays. And instead of affecting two different rows, you can actually affect around more than 3,000 rows in 3 consecutive subarrays. This is some strong experimental results in the literature now, and it shows that the blast radius of RowHammer is increased quite a bit with this kind of attack pattern. It's another type of read disturbance essentially, and it requires more work on understanding the vulnerabilities of memory chips. And for that, I'm not going to go through this, but yeah, this is more motivation for me to conduct more tests on real chips and find better ways of performing these chips, and if possible, even crowdsourcing this testing effort so that we can have better understanding of the vulnerabilities in memory and in processors in different levels. There's another paper published in July in DSN showing that this emerging architecture called processing in memory can be used to form covert and side channels, for example, in an easier way. And it also requires tackling security issues that came with the emerging architectures like processing in memory. Today, our security practices in the products are still designed in a processor-centric way, but the actual processing is quietly shifting to near data. So we need to revisit some assumptions here. So we have more things to do in that front as well. So to tackle or conduct all this research, I'm building a new team at CISPA. So this is the current members of team, and we have like a lot of collaborators. I guess Zulal is also here at the very end because of the alphabetical order. And I'm happy to have more collaborations, especially with people at Bilkent. And to reiterate, this is where I am in the world map. It's in the West Germany, and I'm happy to have some of you there. And I'm looking for motivated researchers at different levels, and some positions are available. And this is the end of my talk. Thank you very much.
Questions? Any further questions? Beyond that.
So with this counter measure with counter, sorry, mitigation with counter values, let's say it's like 4, and then like you did like 4 axes to the same row, and then the counter value is refreshed, and the next axis is slower than usual, right? For that specific row. Is this like one of the parts where there's a timing section?
Yeah. So
Because normally when you like access a row, you have like similar access times.
yeah.
But when you need to do the refresh, it's like slower.
Yes, exactly. So it induces latency of around like 100 nanosecond or something like that.
Mhm.
So you can easily see that jump in the memory access latency.
And the second question is like more general one. Does like these new unified memory architectures affect how like RowHammer behaves, or is it like harder or easier to do? Because like now the pages like move across to different buses between like CPU and GPU.
So
Is there any like
I think it's quite orthogonal because RowHammer is a problem that exists in the physical level in the circuitry, and basically what you explain is more in the like how we manage the data layout or things like that, right? So it's data placement. So as long as the device you place your data has this kind of circuitry underneath, then RowHammer problem exists over there as well. And it also there are some works showing that in the emerging memory technologies, in like resistive memories, for example, or the STT MRAMs, there are similar issues. Even the flash memories, actually, the read disturbance is a like well-known, well-studied phenomenon. Sure.
This might be again a naive question, but I think it was in slide 72.
72.
Yeah, you showed the results with the BreakHammer and the transmitter. So what I would have thought that the result with the no defense would perform best, but applying the defense mechanism with a BreakHammer is even better than that.
Yeah, because in the no defense case, the system doesn't know anything. It doesn't have the notion of like one of the threads being an attacker and performing some malicious operations. So the attacker is not like throttled at all. So it can access memory and it can induce latencies to the memory accesses to other concurrent applications. But here in BreakHammer, since we throttle it, we open up more memory bandwidth for the concurrent run in other benign applications. So that's why it reduces the latency and increases performance. Thanks.
So this is a question kind of, I guess, building up on like RowHammer's question. So like you mentioned unified memory architectures, and you said like that's orthogonal to RowHammer, but like RowHammer type vulnerabilities, read disturbance. But like my question is like are there like new class of vulnerabilities that like you result in RowHammer type attacks that's like result from, instead of having one memory controller, like let's say 2 memory controllers accessing the same memory in a unified architecture, because GPU has its memory controller, CPU has its memory controller. Does that still affect it in any way, or is that still orthogonal?
Okay, so thanks for the correction. I wasn't supposed to say orthogonal because it can make things worse in that sense, yes. So I guess it's like in BreakHammer's case, it's one of the inherent weaknesses of BreakHammer actually, that if 2 different sources of memory accesses are collaborating with each other to perform some attacks, right? And they can keep low profile and unhammered rows.
I guess you can have like multi-device wave attack or something.
Yes.
Like CPU and GPU both hammering, so
yes.
you can detect it.
Yeah. Actually, from the offensive side of the research literature, There's a paper that actually talks about that. I think it was called like ground pounding unit, something like that, that abbreviates to GPU, that uses the GPU's memory accesses to accelerate RowHammer attacks in system level.
Like GPU is like more natural hammer, right? Use because you need to do it fast. Let's say you have like short amount of time. Yeah. Let's say you have like a short amount of time that you have to optimize the device.
Yeah.
And if the GPU and the CPU has isolated memories on their own, it's like a better attack to have unified memory because we can use we can choose which hammer to use.
Yes.
For the
Yes.
same memory.
Yeah, that's true.
I see.
But it's true and false at the same time though, because like in general, GPU's memory accesses tend to be more like stream-like pattern, right? Then there's a high row buffer locality, but actually you can also craft more irregular accesses over there as well.
Yeah, but maybe it's not that like direct.
Maybe you need to engineer it a little bit and it works.
I see.
Any other questions?
No one has one. Like, can I ask you to, like you said, it's mentioned on BreakHammer paper, but like, if you have time, can you elaborate a little bit on like how this works when we don't assume that the attacking code is pinned to a specific physical core? So then, how does BreakHammer work with software threads? Because the attacker can jump between physical CPU cores and when running on the noise.
Yeah. So the difference between software thread and hardware thread is that during the context in which you attribute a software thread to a core, right? So what we do so far in BreakHammer's case is that we sort of store the memory access patterns and the behavior of that, like whatever scores we have, but we attribute it with the software thread. So when a context switch happens, that score is also stored somewhere. And then when it comes back to any core, that it comes with scores. So we sort of like have some memory across context switches for software threads. But that's just that, and there's already an open weakness. Like it's a huge weakness of BreakHammer. It just assumes that everything is in the hardware level, like in between two context switches, like within a session, I'll do this. Now we're working on more hardware software co-design extensions, like operating system extensions of that.
I was gonna say, is that implemented at the kernel level right now, like OS kernel?
If you look at BreakHammer paper, there's nothing about kernel. There's nothing about OS. We are working on that.
It's all bare metal.
Yes. It's just because like we couldn't do everything in one paper, so now we are building on it.
That's for sure. I see.
Yeah.
And not do it you want. Let's thank you.
Thank you very much.